Good morning, good afternoon, and good evening. I'm Tom McNulty, and I'm here with our presenter, Aya Takase. Thank you all for attending Rigaku's webinar series, X-ray Computed Tomography for Material Science. This is our third segment, Food and Pharmaceutical Applications. It will focus on the principles, techniques, and researches used to develop optimized foods, pharmaceutical science applications. Before we start, a few housekeeping items. When today's presentation ends, you'll automatically be directed to a Rigaku webpage containing links for the previous two webinars. Now, as far as today goes, as usual, we will be taking questions during the live webcast. We ask that you submit your questions via the Q&A button on your screen. We will not be monitoring the raised hand or chat features. We will be saving your questions submitted during the webcast, and we'll answer as many as we can during the Q&A session at the end of the presentation. If for whatever reason you have difficulty viewing the webinar live, please note it is being recorded and you will be able to view the recording beginning tomorrow. Okay, that said, I'd like to introduce our speaker as usual for today, Aya Takase. Welcome, Aya.
Thanks, Tom. Thank you everyone for joining us for the webinar series, X-ray Computed Tomography for Material Science. Today, we will talk about food and pharmaceutical applications. So there is something about microscopy nobody told me when I was getting into it. And I think that this is a case for any microscope, not just X-rays. And the thing is that once you start using a microscope, everything starts looking like a potential sample interesting to scan. For example, I would look at my phone and think, oh, I can scan this. This could be interesting to look at. And I can look at insects or rocks or pebbles. And of course, you can look at those tablets, capsules, or grains, candies, all different kinds of food. Those are all very interesting subjects to look at using Xray CT. So many of them make their way to my lab and I scan them. And today, you will see Xray CT images of those samples. Maybe not the spider. I guess that will be for another webinar. So in this webinar, you will learn some keys to imaging soft materials, such as food and drugs. And you will see a number of food science applications and pharmaceutical applications. And I'm putting food and pharmaceutical samples kind of in the same category. And that is because there is something in common between them. So what's in common between food and pharma samples? Well, they are mostly organic compounds, and that means they are mainly made of carbon, which is low atomic number or low Z element. But why does it matter? As we discussed in the first webinar, X-ray CT is an X-ray absorption imaging technique, and X-rays are almost exclusively absorbed by electrons. So the atomic number or the number of electrons you have in a given volume matters. For example, if you use medical X-rays to look at your hand with a nail going through it, it would look like this. The nail is high Z because it has a lot of iron. And the bones, let's say, is medium Z because you have quite a bit of calcium. And you have tissues, which are low Z. And medical X-rays, or more importantly, the energy of X-rays they use is optimized to see the details in the bones, medium Z. And that means that energy is not necessarily optimized to look at the low Z tissues or high Z nail. So one of the keys to note is when the X-ray energy is not optimal for the sample you're looking at, you don't get good contrast. If you optimize the energy, then you can create good contrast and see a lot of details in the sample. In terms of picking the right energy, the electron density of the sample matters, and the sample size matters too. So the general rule of thumb is when you have a small and low density sample, you want to use low energy X-rays. And when you have a large and a high density sample, you want to use high energy X-rays. And food and the pharmaceutical samples are usually in the small, low density category. So we want to use low energy X-rays. So that much we know now. But how do you get low energy X-rays? What determines X-ray energy to begin with? So let's think about this for a minute. If you're using a lab-based X-ray source, X-ray generator, as opposed to synchrotron radiation, there are two types of X-rays, or I should say there are two mechanisms for X-rays to be generated. One is called Bremsstrahlung radiation, and the other one is called characteristic radiation. The energy of X-rays in both cases depends on the X-ray target material, applied voltage, and the filter. To understand how X-ray energy depends on those three parameters, let's take a look at how X-rays are generated. So this is a schematic diagram of an X-ray generator. You have a filament, which is the cathode, and you have a target, which is the anode. And you would apply high voltage between the filament and target, then put some current through the filament, then thermal electrons would come out. And they will be attracted to the target because of the high voltage applied between the filament and target. When those electrons hit the target, X-rays are generated. Now the question is, what kind of energy distribution do we have with those X-ray photons? So let's take a look at an example. If the target material is tungsten and you apply 130 kilovolt or kV, and let's say we put 1 millimeter thick aluminum filter, then the energy distribution would look like this. The x-axis is the X-ray energy, and the y-axis is the relative X-ray intensity. And you notice that there are some sharp peaks, and those are called characteristic radiations. You also have a broad peak, and this is called Bremsstrahlung radiation. And usually there is a combination of those two, creating kind of complicated energy distribution in the low energy range. And that is cleaned up by adding a filter. So let's take a look at the Bremsstrahlung radiation first. How is this generated? So those thermal electrons, they travel in vacuum and eventually they hit the target. Let's assume that the target is tungsten. And the tungsten target has a lot of free electrons in it. So those thermal electrons, as soon as they hit the target, they have to slow down. And when they slow down, they have to convert their kinetic energy into actually mostly heat, but partially X-rays. And because this process happens gradually, different electrons slow down at different rates. The resulting X-rays have wide range of energy. And this is called Bremsstrahlung radiation. Sometimes people call this either continuous radiation or white radiation, again, because of the wide range of X-ray energy. If you do a relatively simplified calculation for this energy distribution, it would look like this. So we're assuming that the target is tungsten, and we're applying 200 kilovolt per kV. And one thing to notice is when you apply 200 kV, your peak energy is about 100 kiloelectron volt or keV. Now, let's think about what happens if you change that applied voltage from 200 to 130, 90, or 60. So you see the trend. The X-ray intensity goes down when you change the applied voltage, but more importantly, the peak energy shifts towards the lower energy side. So this is one of the things you can do to get low energy X-rays. So this is a calculation for tungsten target. But what happens if you change that target to something else? So this calculation is for tungsten target. By the way, tungsten's atomic number is a 74, so it has a lot of electrons in it. and we're applying 60 kV. If you change this tungsten target to molybdenum number 42 or copper number 29, you see that the X-ray intensity goes down, but the energy distribution does not change. So when you use lower atomic number metals as a target, because you have fewer electrons, you lose X-ray intensity. But peak energy doesn't change, so it doesn't make any sense to change the target material to those lighter metals. So tungsten is a good target to use if you're going to use Bremsstrahlung radiation. And that is why tungsten is one of the most used or widely used X-ray target material. Now, let's take a look at the filter next. I said that this part is cleaned up by adding the aluminum filter. But what happens if you change that filter to something else? So this is a calculation for tungsten target, 130 kV applied with 0.2 millimeter copper filter. Again, we're just looking at the Bremsstrahlung radiation for now. If you change this filter to 0.1 millimeter copper, the energy distribution shifts. If you change this to aluminum and make it thinner, it keeps shifting. And the trend you see here is that X-ray intensity goes up when you change the filter to lighter, thinner material. And also the energy distribution shifts towards the lower side. So this is another thing you can do to get low energy X-rays. To summarize, if you're using Bremsstrahlung radiation, you can use high atomic number targets such as tungsten, and you apply low voltage and you use light and thin filter to get low energy. For example, if you have tungsten target, apply 60 kV and put 0.5 millimeter aluminum filter, your energy distribution looks like this, and your peak energy is about 30 keV. You have a relatively wide range of X-ray energy. Nonetheless, this is a pretty low energy X-rays you can use. Let's take a look at the characteristic radiations next. So how are those radiations generated? So those thermal electrons, again, they travel in vacuum and they hit the target. And the tungsten target has free electrons, and it also has inner shells, like K shell and L shells, and you have electrons in them too. And if those thermal electrons have enough energy, to be specific, in this case, greater than 69.3 keV, then they can knock out those K shell electrons out of their orbits. And when this happens, another electron in the K shell sees an opportunity to get to a supposedly better place. And when this happens, this originally L shell electron needs to give up its potential energy to get to the L shell. And this potential energy difference is 59.3 keV in this case. And this energy is released as X-ray photons. And because of the energy of those X-ray photons is specific to the target material and the shell combination, those are called characteristic radiations. When you have tungsten target and look at one of the strongest K radiations, you would see 59.3 keV. If you change this to molybdenum, you can get 17.5 keV, and copper would give you 8, and chromium would give you 5.4. So you can see that by using those target materials and the characteristic radiations, you can use very low energy X-rays. And the strategy to get the right energy in the case of a characteristic radiation is pretty simple. You just choose the right target for the desired energy. For example, if you want to use, let's say, 8 keV energy, then you would use copper as your target material. Then you can apply 40 keV or even higher voltage to get high intensity. without worrying about shifting the energy of the X-rays because this 8 keV is characteristic to copper. Its distribution is pretty narrow, and you are going to get some Bremsstrahlung radiation from copper as well, but its intensity is pretty low compared to the characteristic radiation. Okay, so if you are using a lab-based X-ray source, you can either use Bremsstrahlung radiation or characteristic radiation. Either way, the X-ray energy depends on the X-ray target material, applied voltage, and the filter. So now you know how you can get low energy X-rays. And I want to show you two examples where using low energy X-ray helps a lot to increase the contrast and get good quality images. This is an X-ray CT scan of a cranberry seed. The whole seed is only a couple millimeters in size. And if you do a scan with copper 8 keV radiation and look at the cross section, it looks like this. So you can see that you see a lot of details with very good contrast, even though this is only a couple of millimeters in size organic material. Now, what if you want to see something even lighter and thinner, like an organic film? So this is an organic film that is only 80 microns in thickness, and it has a 3 micron thick membrane filter embedded in it. And since the membrane filter and the sandwiching films are both organic materials, there is not a whole lot of density contrast between the two. And the whole thing is only 80 microns thick. So if you use traditional tungsten target Bremsstrahlung radiation, even if you lower the applied voltage down to 35, you really don't see anything in the projection. But if you use chromium target and the characteristic radiation at a 5.4 keV, then you can clearly see the pattern coming from the organic membrane filter. And this is just a 2D projection, but you can do full CT scan and look at this film in 3D. And because we are using low energy X-rays at a 5.4 keV, you can clearly see the difference of the sandwiching organic films and the membrane filter, and you can see some fillings as well. Okay, so the key to remember is most of the food and the pharmaceutical samples are low density and small. So you want to use low energy X-rays to get good quality images. And you could either have tungsten target, and in that case, you can lower kV, apply the voltage, and use less filter, or you can select the target on your generator. And if that's the case, you can use elements such as molybdenum, copper, or chromium, and use their characteristic low energy X-rays. So let's take a look at some examples. What can we do with CT technique for food applications? Now, when you look at those review papers talking about how people use X-ray CT for food science, there are a whole lot variety of things people do. And the list I'm going to show you here is only a small part of it. So for example, you can look at meat fat distribution in either raw meat or processed meat. You can look at breading of deep fried food and see where the frying oil gets stuck in the breading. You can look at various coatings. You can visualize freezing process. You can look at sprouted or infested kernels. And another thing that people use CT technique for in this industry is the classification or identification of phenotypes. Since X-ray CT is a non-destructive 3D imaging technique, you can use it to look at seeds, grains, fruits, or all different kinds of plants in 3D. And that is a convenient way to classify or identify phenotypes. So that's one of the applications. So let's say that we want to look at salami. And I would like to walk you through the whole process of picking a sample, setting measurement conditions, doing a scan, and getting some analysis results. So we said that we want to look at salami. And you want to take it out of the fridge. And one of the questions that might come to your mind at this point is, how thick of a slice should I cut? And that's probably one of the many questions that will come to your mind if this is your very first CT scan to run. So there are a couple of things to consider. One is the sample size. And usually the sample size is close to the field of view, or FOV. And the FOV more or less dictates what kind of resolution you can get. And that resolution would tell you what kind of geometry to use, meaning either the cone beam geometry or the parallel beam geometry. And the sample direction is important too. Depending on the sample shape or aspect ratio, this is an important parameter to think about. And of course, the X-ray energy. The sum of those parameters are related to each other, and they are in kind of a trade-off relationship. For example, those three are related to each other and they kind of restrict each other. Even the X-ray energy, if you try to use low energy, sometimes you lose X-ray intensity and that can make your scan time very long. So for all those parameters, it's important to hit a good balance of those parameters. Let's take a look at the first four because those are all related. First parameter, the field of view, FOV. Let's say that randomly we pick 5 millimeters as the field of view for the salami. Then it would look like this. So you kind of see 2 or 3 phases in this 5 millimeter view, but those are really big chunks. And this means that this sampling size is not big enough. You're not going to get statistically reliable results from this tiny view. So we need a larger field of view. So let's go with 30 millimeters. So this looks more like it. We clearly see 3 phases, and each phase has multiple pieces or chunks that should give you better statistical results. Now, let's think about the resolution next. So the voxel size, that is your resolution. And let's say that we're going to try 100 microns. Then it would look like this. We can see different phases, but this looks pretty pixelated. So we probably want a little bit higher resolution, like 30 microns. So this looks a lot better. So let's go with 30 microns. So we have parameters as FOV 30 millimeters and the voxel size 30 microns. And this is not that high of a resolution, so you can use the cone beam geometry. Now, how big of a file is this gonna be? This is something to keep an eye on because you can easily do 20, 30 gigabytes of scans all day long, and that's gonna take up your disk space very quick. And you might even have a hard time visualizing the results or analyzing the results later. So file size is something to keep in mind before you start a scan. Let's see how big this one is going to be. So you will have X pixels cube as the reconstructed volume, and each pixel or voxel has 16-bit deep gray level information. X can be calculated as 30 millimeters FOV divided by 30 microns voxel size, and that is 1,000. This means the file size is going to be X cubed times 16 bits. That is 16 times 10 to the 9th divided by 8 bytes, and that is 2 gigabytes. So that is a very reasonable size, probably an average, maybe on the smaller side for X-ray CT scan. So you're not gonna have any problem visualizing the results or analyzing it. So this looks all good. Now, let's move on to the next one, the sample direction. So you have a slice of salami, and you can put it on the stage like this and shoot X-rays and rotate it like this. Or you can put the salami on the stage like this and shoot X-rays and rotate it this way. If the aspect ratio of the sample is close to 1, both of them probably will give you decent results. But if the aspect ratio is kind of far from 1, then this is not an ideal way to put the sample on the stage. This one is preferred. But why is that? So if you put the sample this way, now we're going to look at this from the top. At 0 degree, X-rays need to go through this much of a salami. At 90 degrees, X-rays need to go through only this much of a salami. So the thickness of the sample changes depending on the angle, and that changes the overall absorption rate, X-ray intensity, and all those things can affect the image quality. So this would be a better way to put the sample on the stage. So we're going to look at this one from the top. At 0 degree, X-rays need to go through this much of a salami. And as you might have guessed, at 90 degrees, X-rays go through the same amount of sample. So this is the direction with the least variable thickness, and this direction is usually preferred. And I'm going to abbreviate this as LVT for least variable thickness for the following slides. So this is a sample direction. Now let's take a look at X-ray energy. So you could have either tungsten target X-ray source, or you could have selectable targets. We're using the cone beam geometry for this salami experiment. So most likely, that means you have a tungsten target. That means our strategy is to lower the kV, apply the voltage, and use less filter. So let's say that we're going to use 60 kV with a thin aluminum filter, and we look at the projection. And when you have this projection at this setting, you don't need to go crazy and change this 60 kV to 61, 62, 63, and see what happens. Because with the Bremsstrahlung radiation, you have a wide range of X-ray energy. Changing 60 to 61 is not going to make that much of a difference. So what you do is you pick one number, like 60 in this case, and look at the projection, and look at the center area, adjust the contrast, and make sure that you see different phases with different contrast. If everything looks too dark at this point and you don't get good contrast, you want to increase the kV, let's say up to 80 or 90. If everything looks too bright and you don't get good contrast, then you lower the kV to, for example, 40, and you might even want to take out the filter as well. In this case, this looks good, so we're ready to do a scan. So we put this salami on the stage, and this one is about 40 millimeters in diameter, which is a little bit larger than the FOV, but they're close enough. We're going to use 30 microns as the resolution, and we can use the cone beam geometry. The sample is in the least variable thickness direction, and we're going to use 60 kV for the X-ray setting. 17 minutes later, we have a scan. So this is an actual X-ray CT scan of the salami we're just looking at. In the cross-section, we see the meat, the fat, and the void. And as we discussed in the second webinar, you can do image segmentation analysis with this result. So this is the original image, and I used machine learning to segment this into 3 different phases like this. And then you can do this in 3D to see where the fat is or the voids are. And in this salami, we have 17.9% fat. That's quite a bit of a fat. But this is the general strategy or flow when you have a sample you want to look at, and this is how you can set the measurement conditions, do a scan, and get some results. And then you can apply the same strategy to look at all different kinds of samples, such as a corn dog. This is the cross-section of this corn dog. You see the stick, sausage, and the breading. You can change the field of view and use higher resolution to look at more details in the breading. So this part is the sausage, and this part is the breading. And this image has been already segmented into those yellow pixels. They represent the frying oil that got stuck in the breading. And the red pixels represent the air in the breading. So you can visualize where the frying oil is and where it gets stuck. You can look at something like chocolate candy as well. Again, this is an actual X-ray CT scan. And you can look at the cross-section, segment the sugar coating. Then once you segmented it, you can do a coating thickness distribution analysis like this. And I don't know why, but those chocolate candies have those yellow spots at the center. And that yellow spot represents thicker coating of 500 microns compared to everywhere else that has 250 microns of coating. This sample has a pretty simple shape, and you can do this type of coating thickness distribution analysis. But you can do the same thing for more complicated shaped samples, like a pretzel. So this is a yogurt flavored chocolate coated pretzel. And you can see the cross section. Those white bright spots represent salt grains. And you can see where those salt grains are in 3D. And again, you can do the coating analysis. So you see some yellow areas around those holes, and they represent 2 to 3 millimeters, a little bit thick coating. And where the pretzel is sticking out, you see blue, that means the coating is thinner. And you can do statistical analysis for overall coating thickness and calculate things like a minimum, maximum, or mean thickness, which was 1.3 millimeter in this case. So those are relatively large samples, but what if your sample is tiny, like C's? The general rule is if your sample is less than 5 millimeters, sometimes it could be less than 1 millimeter, then your FOV is going to be as small. And this means that you're going to need sub-micron to 1 or 2 micron resolution. And this means that the parallel beam will work the best to achieve this resolution. The strategy for the sample direction does not change. And for the X-ray energy, now we're talking about only a couple of millimeters in size organic material. So you want to go lower to 5 to 8 keV energy, and that is usually characteristic radiation. So this is an example of a sesame seed. We're going to scan this with a 3 millimeter FOV with a 1.3 micron resolution, and we use the parallel beam geometry with 8 keV copper characteristic radiation. And this is what the scan looks like. If you look at the cross section, although this is all organic, only a couple of millimeter in size sample, you can see all the details in very good contrast. And I didn't notice until I scanned a couple of sesame seeds, but they all have a very high density surface layer, like the white line you see in this cross section. And once you have this image in 3D, you can do different types of analysis, such as separating the solid part and calculating the Boy's percentage, or you can focus on this high density surface layer, the skin. And when you do the thickness distribution analysis, you can see that at the bottom and around the neck area, you see thicker skin. And you can do this for, let's say, one type of sesame, sesame A, which has thin skin and large voice. And you can do the same thing for a different type of sesame seed, sesame B. This one has thicker skin and a smaller voice. And this is a type of visualization or quantitative analysis you can do to compare different phenotypes and classify them or identify them. Okay, so we looked at a number of food applications. Now let's move on to pharmaceutical samples. What can we do with a CT for those samples? The typical applications people use X-ray CT in the pharmaceutical industry includes imaging of cracks, aggregates, or coatings. I guess those are more important than chocolate coating on the pretzel. And you can see crystallization process or dissolution process as well. And if there are any contamination or foreign materials mixed into those tablets and bottles, you can of course see them too. Now, speaking of contamination, can you see a whole bottle? And yes, you can, because we're using X-rays. So this is a just two-dimensional projection of a whole bottle that has capsules inside. And this type of a 2D projection is usually enough to find those foreign materials. And this image was collected at 90 kV with tungsten target and 107 millimeter FOV. And you can use the same machine, just change the voltage to 60 and FOV to 25 millimeters to scan an individual capsule and get a 3D scan like this. And the general strategy is very similar to what we saw for food. If we have relatively large sample, like this whole package with the tablets inside, you would use tungsten target with a relatively large field of view. But if you want to look at an individual tablet in more detail, you would switch to lower energy, such as copper 8 kV, and use a smaller FOV, 7 millimeters in this case. Then you can do a scan with a higher resolution to see multiple coatings, cracks in different phases. Sometimes you might even use two different settings to look at one kind of tablet. So this tablet was a scan with molybdenum 17.5 keV with 10 millimeter FOV setting. As you will see, this tablet has multiple particles inside, and each particle is only 0.5 millimeter in diameter. If you want to see more details in those particles, then you would switch to chromium 5.4 keV, even lower energy, and use 0.7 millimeter smaller FOV. Then you can use, in this case, less than 0.3 micron resolution to see multiple coatings and cracks in different phases and voids inside of a 0.5 millimeter diameter particle. Okay, so let's take a look at some tablets. This one is an aspirin tablet. So you have aspirin, and you also have hydrothalcite layer. And you can see that the hydrothalcite layer thickness changes quite a bit, and you have some cracks inside too. If you look at this corner closely, you see about 50 micron thick coating and up to 90 micron in size gap. So you see delamination of the coating in this case. And this type of details can be easily observed by using X-ray CT. You can compare different tablets like this one. So this is a famotidine tablet. We call this tablet A. This one is very clean. You don't see any aggregates or cracks or anything. But the same famotidine tablet B looks like this. So you have a pretty big crack in the middle. Now, tablet C, I don't know what happened to this one, but shows big sized phase change. And also you see some kind of black speckles inside. And those black speckles indicate that you have voids inside of the tablet. And X-ray CT is a non-destructive imaging technique. So you can see this type of change without breaking those tablets. And that means that you can monitor one tablet and you live in a certain environment for hours, days, or weeks, and continue to monitor what kind of changes happen to that tablet, including phase changes, aggregates, and creation of voids. And you can see this type of phase change or voids or aggregation whenever you have density change. As far as you have enough density difference, you can always image them with X-ray CT. But how big of a density difference is enough? So let's take a look at an example where you see very small difference. This sample is a small piece of polyethylene, and this was scanned using chromium 5.4 keV radiation. It might be a little bit difficult to see in this image, but the top part is made of high density polyethylene of 0.93 grams per cubic centimeter. The bottom part is made of low density polyethylene of 0.88 grams per cubic centimeter. Both of them are very low density, light absorbing materials to begin with. And the difference of the density is about 5%. If you see the histogram of this image, it's very clear that the low density and high density polyethylene phases have clearly different gray levels. This means that you can easily segment those two and do whatever quantitative analysis you want to do. So this gives us an idea that the 5% is probably enough for us to see the difference between different phases. Now, this means that you can see things like crystallization as far as there is enough density difference between amorphous and crystalline phases. So let's take a look at an example. Those tablets have a small amount of crystallized API, and the density difference between amorphous and the crystalline phases was about 8%. And you see the crystalline phases as those yellow bright spots. Because there is really good contrast between the crystalline phase and the matrix, you can easily segment it. They're colored in red in those images, and you can calculate the volume percentage of a crystalline phase. And if you know the density of this phase, you can convert those numbers into weight percent. Those tablets actually were made by spiking them with a known amount of crystalline phase, and the spiked amounts were 0, 1, and 3%. Considering that the spiking and the mixing process is not necessarily perfect either, those numbers show very good match. And this means that not only that you can calculate percent crystallinity using X-ray CT, you can also see where that crystallization is happening. Are they starting from seed crystals that were already in the original tablet, or is it starting on the surface where it's exposed to humidity? You can tell the difference between those two using this technique. Now, I want to change the subject a little bit. I don't know how many of you use generic brand drugs, but are they really the same as brand name drugs? So there are a group of people who looked into this. Those are dissolution curves for certain medicine, and this was published in Journal of Drug Delivery Science and Technology. The x-axis is the time, and the y-axis is the percentage of drug released. This line is the golden standard coming from lipitor. So this is the brand name lipitor cholesterol medication. And the other curves are coming from generic versions of a lipitor. And most of them actually are pretty close to lipitor, so that's good to know. But to claim a certain medication or drug is a generic version of lipitor in this case, you have to reach 80% release at 15-minute mark. And when you look at this graph, you realize that this one is barely passing the test. And this is one of the generic versions of a lipitor. So both of them qualify as lipitor, but it's pretty different. So let's see X-ray CT images of those tablets to see if we notice any difference. First, lipitor. So this one is a tablet made by Astellas, which is licensed by Pfizer. So this tablet looks very clean. Different phases are mixed very uniformly. You don't see any aggregates or cracks. So this is lipitor. Now let's take a look at that generic brand. So this is what that one looks like. So this tablet has pretty non-uniform mixing of different phases, and you see pretty large aggregates indicated with yellow arrows in this paper. And this might not look like much, but those aggregates can change the release rate or dissolution curve quite a bit. And you can always measure the resolution curve or measure the release rate, but until you actually see it, you don't know where that difference is coming from. So this is an example of generic and brand name drugs. But what about those premium and store brands? Do we see difference in those? Well, let's take a look. Those are painkiller tablets. This one is a premium brand painkiller, and this one is a store brand. Both of them are labeled as rapid release. And those gray bands supposedly have something to do with the rapid release. So let's take a look at them with Xray CT. So this is a scan of the premium brand, and clearly there is something going on here. If you look at the cross-section of this tablet here, actually it's very clear. So the tablet has high density coating, but the coating has those openings. It has holes, and those holes are exposing the internal drug. So this should help rapid release. That makes sense. You can look at this coating thickness, and the yellow means thick and the blue means thin. And if you look at this one from the side, again, it is very clear that this coating has an opening. If you look at the corner of this tablet closely, you also realize that there are two layers of coating. You have one layer on the outside and another one on the inside. So this is the premium brand. Now let's take a look at the store brand. So this is a store brand tablet CT scan. There is something going on here, but it's not as clear as before. We can look at the cross section here. Then you realize that this coating is everywhere, and we don't see any opening or hole in this case. We can look at this from the side, and again, there might be something going on here, but it's not very clear. If you compare those two brands, actually the difference is pretty clear. So the premium brand has the coating, and the coating has an opening for rapid release. The store brand has the coating everywhere. It has some sort of cap or cover on top of the tablet, but you can tell this is not a coating, but it's just a cover because there is a huge air gap. So they look very different. If you look at their corners, the difference is even more clear. The premium brand has two tight coatings, and the store brand has just one coating with some sort of cap going over it. And this is a type of difference, another type of difference you can easily see with Xray CT. Now, we've been talking about dissolution curve or release rate, and this kind of brings us to this question. Can you see change over time? Can we monitor the change by using Xray CT? Yes, you can, and I want to show you two examples. The first one is a tablet that was left in a hot and humid environment for 2 weeks. So this is a tablet we used for this experiment, and this one has a pretty intricate structure to control the release rate. So it has this rapid dissolving matrix surrounding the slow dissolving shell, which is surrounding the API. And all those three phases are there to control the release rate. And at the beginning of the experiment, all three phases are there intact. But we're gonna leave this in 60 degrees, 70% humidity environment for 2 weeks. Then this is what it became. All those black spots you see in this tablet are voids. So you can see that not only the rapid dissolving matrix, but the core API has dissolved as well. So this is a change you can see in 2 weeks. The last example I want to show you is a change that happens a little bit quicker. So we're going to drop one of those painkillers in water and see what happens in 44 minutes. So this is the premium brand painkiller. And remember that at the center area, you have those holes for rapid release. But if you look at this part, it's fully coated and you have 2 layers of coating. Those cross sections are showing 0-minute dry state. Now we're gonna pour water over this tablet and see what happens. So 4 minutes later, this is what they look like. The rapid release part released the drug rapidly as it's supposed to, so you don't see any coating anymore. But for the fully coated part, you still see the coating almost intact. So this is 4 minutes. So we're gonna keep watching. This is 8 minutes, 12 minutes, 16, 32, and 44 minutes later, now you see this layer dissolving. This is a change that happened in 44 minutes, and this happens pretty fast, but you can still see it. And of course, when you see something that happens in 30 minutes or an hour, you have to do your CT scan pretty fast. And those cross sections you just saw were collected in 4 minutes each. Okay. So those are the typical applications people use X-ray CT for in the pharmaceutical industry. And we looked at a number of food science applications today as well. And I hope you find them interesting. And when you go back to your lab, you find something interesting to look at. So you just learned some keys to imaging soft materials. And we looked at food science applications and pharmaceutical applications. All the images you saw today were collected on the Rigaku X-ray CT scanners. If you would like to learn more about them, please contact your local sales representative or go to rigaku.com and contact. This is the end of the third webinar. Next on X-ray Computed Tomography is going to be about foams and composites applications. It'll be on December 11th, Wednesday at 11 a.m. Pacific Standard Time or 2 p.m. Eastern Standard Time. I have one more announcement I would like to make before we get to the Q&A session. We will have an X-ray microscopy seminar and a workshop at the Rigaku facility in the Woodlands, Texas. It is on October 30th, Wednesday, and it is one-day event, and we will have invited speakers from the Dow Chemical Company, Clemson University, and Object Research Systems. We will go to the lab and run some CT scans and do data analysis in the workshop as well. Tom will tell you where you can go to register at the end of the webinar. Thank you.
Okay, thanks, Aya. Very, very interesting. And thank you so much for presenting. It appears we're going to have some time for Q&A. We have a couple of questions that have already come in. First question from John in California. Is it possible to run a sample that is larger than the FOV? For example, a tablet or capsule. And if so, what are the negative effects, if any?
So you can run a scan with the FOV that is smaller than the sample. And your sample can be, I'm going to say, about 2 or 3 times bigger than the FOV, that you can still get an image. The side effect is the bigger the sample is compared to the FOV, probably you will see higher noise level, which you can compensate by spending longer time to do a scan. And also you can do multiple scans to cover different areas and stitch them together to cover a bigger sample.
Okay. Next question comes from Diane in Massachusetts. Says, I've noticed that most of the images you have collected were run with copper or moly. What type of samples would you anticipate chromium giving the best images?
So chromium has lower energy compared to copper and molybdenum characteristic radiations. So it would work well when you have lighter, smaller samples. Actually, there were 2 examples we looked at today. One was organic film that was only 80 microns thick. That one looks the best when you do chromium radiation. Also for pharmaceutical applications, if you want to look at an individual particle that is only 0.5 millimeter or even smaller, because there is not much sample to absorb X-rays, chromium radiation works very well.
Right, okay. Well, that seems to be all the questions that we have today. So if any more come in, you can send us by email, and we can try to get back to you. Okay, so as I said, recording of this webinar will be available tomorrow. An email will go out to all the registrants with instructions how to view the recorded presentation. After the close of the webinar today, you'll be automatically directed to a landing page on the Rigaku website with a link to the next webcast, which will be applications in foams and composites. Note that Zoom may interrupt the transfer to the landing page with a request for you to participate in a survey. You can just click continue, and then that will take you directly to the landing page. Note also that the page contains the links, as I said before, to the two previous webinars, and as well a link to the Houston seminar that I mentioned during the presentation. So you can register for that on that same page. Okay, well, thank you for joining us, and we will see you next time. Bye-bye now.